Righto, okay, so then I am going to go on to chapter 5. Hopefully we can make some progress there before the end of the session. I will put up the slides on the classroom, or I say on the classroom, on the chat room as well. You guys can go get it there as well. Okay, so yeah, so we're first going to take a look at the behavior of RC circuits and RL circuits. Um, so yeah, so right. Okay, so you guys should know by now, capacitor is a component that will store electrical charge or will store energy in the form of electrical charge. And and there are three main internal factors that will influence the capacitance of a capacitor. So basically physical properties of the capacitor. So that's going to be the dielectric constant. So the material that's being used as a dielectric is going to determine the capacitance. So for instance, plastic is going to be much better than air as a dielectric. The cross-sectional area of the plates. So in this case, the bigger the cross-sectional area, the bigger the capacitance. And then the distance between the plates. So, but that relationship is inverse. So meaning the closer the plates are to one another, or the shorter the distance between the plates, the bigger the capacitance. And we can express the capacitance of a capacitor then with this formula here. Now you guys will see something here. It looks like it's number of turns, but it's actually the number of plates, right? So that's N minus 1. So you guys will see if you go look up or just Google air capacitors or adjustable capacitors. How those capacitors work is they basically just have a bunch of plates shifting in between one another. Right, so that's where that formula then comes in with that N minus 1. So if you have two plates, that's then 2 minus 1, so that just becomes 1. Okay, again, charge accumulation. So charge accumulated by a capacitor would just be the capacitance times the voltage applied. And the voltage applied is just considered an external factor. So you guys will see the bigger the voltage, the more charge will be stored. And yeah, so the energy stored on a capacitor when fully charged is just the capacitance multiplied by the applied voltage squared divided by 2. And this energy is measured in joules. Okay, so let's take a look at what will happen if we build a circuit that will look something like this. And we have a DC source here. It can be an AC source as well. You're going to have similar behavior, but DC source will show this a bit better. So this is pretty much going to be an introduction into transient theory. Right, so it's something that you guys are going to do a bit more in 6. We're not going to really focus too much on it in 5. Right, so essentially what we're going to do here is we're going to close the switch, and you're going to have this capacitor then will start to take up charge. Right, so the time that it will take the capacitor to charge to within 63.2% of the maximum supply voltage is known as the time constant. We calculate that time constant by taking the resistance multiplied with the capacitance. That will give you a time in seconds. So also further that we can take notice here, in fact we need to look at the graphs for this, is that the time taken for the voltage across the capacitor to reach the supply voltage is also called the transient response. And yeah, so yeah, it's a transient response, or the whole action of that happening. And then it takes approximately 5 time constants for the circuit to reach steady state, meaning that there's no changes occurring in the circuit anymore. Right, so if we take a look at these graphs, they actually show it very nicely. So it's an exponential increase in voltage and an exponential decrease in current. Right, so you guys will see the voltage across your capacitor will follow a curve like this. So the voltages are going to increase exponentially, and then it's sort of going to flatten out after 5 time constants. Right, so there is one time constant. You guys will see that's 63.2% of your maximum supply voltage. 4 time constants, that's about 98% of your full supply voltage. And then at 5 time constants, we consider the capacitor fully charged. From there on out, you don't really have any changes occurring. Now, with the voltage across the resistor and the current in the circuit, that's going to decrease over time as the capacitor gets charged. Right, so the capacitor essentially, how can we say this? The charge saturates the plate. So you're going to reach a point where there's not going to be any current flow anymore. So current is going to decrease, and again, after one time constant, the current would have then been decreased by 63.2% of the maximum current, and that will continue to decrease up until zero, very close to zero, up to 5 time constants, after which we consider the circuit to be at steady state. Right, so our initial conditions, time is going to be equal to 0, capacitor voltage is going to be equal to 0, the voltage across the resistor is going to be the same as the supply voltage, and the current is also going to be a maximum. In fact, that maximum current is, sorry, that's the supply voltage divided by the resistance. Right, and at any point in time, the sum of the resistor and capacitor voltage will be the supply voltage. So if I look here at 2 time constants, for instance, so the voltage there and the voltage there, if we add those two together, that's going to give you your supply voltage. Right, so if the supply voltage, yeah, okay, so that's going to give you a supply voltage. I just noticed there are no supply voltage values here almost. I wanted to do that. But in any case, that's pretty much what you're going to have there. Right, so when a charge, that's known as discharging. So typically what a circuit will look like for that is you will have a fully charged capacitor. We short circuit the source. Current is now going to flow in the other direction. So we're going to consider the current to have changed polarity, so thus a negative current. And essentially what that looks like is that the capacitor voltage is going to start out at a maximum, and that's going to decrease towards 0 over time. But the current here is also going to start out at a maximum, but it's going to be of opposite polarity, and that's also going to decrease over time towards 0. Again, the same rules are applicable here in terms of time constant as we had with the charging circuit. So during discharging, when the capacitor has lost 63.2% of its charge, that happens at one time constant, as we can see there. So it lost 63.2% of its charge, which means it has 0.37. I think I see 0.37 here, but I think it's more like 0.368 percent there, or 36.8% charge left on the capacitor. So yeah, so it lost 63.2% of that charge. And yeah, so essentially, if you do a charge and discharge cycle back to back, so that's what it's going to look like charging and then discharging, so the voltage of the capacitor. So you can essentially imagine this as your source. So your source is basically a pulse like that. You can do the same, yeah, so you can see the same thing with the current if that is your input voltage. then your current is, yeah, so here things are the right way around. Yeah, so current's going to start at a maximum, go to low, and then start at a maximum again when the capacitor discharges, but do that. Okay, so that's your RC circuit. Okay, so quick and easy there. All right, so with that in mind, we can do a few interesting things. If we use an input voltage that's a square waveform. So the first circuit that we can have here is an RC differentiator, also called an approximate differentiator. So the output, so the output that you're going to get for a rectangular input is then equal to the rate of change of the input voltage. So yeah, so you guys, yeah, so the reason why we get these sharp pulses, because essentially the slope of the square waveform there is infinite, theoretically, so that you can get those sharp pulses. And you guys will see a RC differentiator also has a very short time constant as well. Right, so the time constant in this case is it's much shorter than the period of the applied waveform. In fact, it's for this particular example, the time constant is almost a quarter of the pulse width, right? So the time constant is probably somewhere thereabouts. Okay, so as you guys can see, it is much smaller than the period of the applied waveform, so that you can get that kind of output. Yeah, so essentially this is going to let through a high frequency noise or high frequency signals. So this is a high pass filter in this configuration. So this is also what the circuit configuration will look like. So we take the output across the resistance. All right, so that's pretty much, yeah, so this is pretty much what we have. And yeah, so again, in order for the circuit to operate effectively, the settling time or the steady state time for this thing needs to be much shorter than the pulse width of the input. So again, we can see that here the settling time of this output is almost half of the input there, or rather half. Yeah, well, the setting time is half the pulse width of the input. You can also make an RC integrator using the RC circuit, but then instead of taking the output across the resistor, we take it across the capacitor. And yeah, so this circuit is then designed so that we have a time constant. So this is the opposite of the differentiator. So we have a time constant here much bigger than the period of the applied waveform. So as you guys can see here, this is pretty much just one time constant here. So 5 time constants are way out there even. So there's 4 time constants. So just to give a bit of an idea how big the time constant is actually actually here. Right. So this is a low pass filter, so it will let low frequencies through to the output. And essentially high frequencies are effectively short circuited. So if we take a look at our capacitive reactance formula, so if the capacitance stays constant, if the frequency goes up, so if frequency tends towards infinity, so it goes higher, then XC will tend towards 0, right? So it will essentially become a short circuit if you have high frequencies applied to the input, which essentially will give you 0 output voltage. And yeah, then at low frequencies, you'll have a bigger output voltage. Actually, should have shown it here as well. So if we use XC equals 1 over 2 pi FC, again, for this one being a high pass filter, So it's actually going to let a higher voltage sit here across the resistance. All right, cool. But yeah, and I think, yeah, just to wrap up the RC circuit, um, so yeah, so another circuit that we have is the RC coupling circuit. Again, take note, we are taking the output across the resistance here again. And yeah, so this is a circuit typically used if we have two amplifier stages that need to be coupled to one another. And yeah, so another thing with this circuit, yeah, so it's essential purpose. So remember, this is in this configuration, we are working with a high pass filter. So we want to block DC signals essentially. That's actually what we want to do here. We only want to pass the AC component of an input signal. Now, I think with the differentiator, we wanted a time constant much smaller than the period of our input waveform. I think here it's just the opposite. So here we need a time constant at least 6 times larger than the period of the input signal. Right. Okay, so that's pretty much it. So you're gonna get a signal like this. So this is your input signal. So as you guys can see, there's a DC offset to the signal. Now to get rid of that, we can use the RC coupling circuit, and that will essentially just give us an output here around 0 volts. And yeah, so you guys will see across the capacitor, there's going to be a little bit of a ripple around the DC voltage. So the DC voltage is essentially going to sit across the capacitor. All right. Okay, guys, I think I'm going to call it here. If there are no, if you guys don't have any questions, have a good evening, and I'll see you guys next week. I'll post the slides on the chat room in a moment. All right, cool. Cheers, guys.